Zirconia, an advanced ceramic that gets tougher when stressed. Today I'm presenting on zirconia, an advanced ceramic known as ceramic steel, because of its remarkable toughness. We'll cover its crystal structures, how phase change it makes it stronger, its processing, and real world uses, especially in clean energy solid oxide fuel cells. Let's start from the very beginning. Where does zirconia actually come from? On the left, you see raw zircon, a brownish material that looks like rough rock or sand. Zircon is the natural mineral source and is mainly mined from beach sand deposits and heavy mineral sands around the world. Next to it is zircon sand, tiny naturally occurring grains that contain zirconium. Then on the right side is the pure white zirconia powder. This powder is created by chemically refining and purifying the zircon sand. The result is high purity ZrO2 powder that we can then mix with a stabilizer like yttria. This white powder is the starting material for all the advanced zirconia ceramics we'll talk about today. Everything begins with mining zircon and turning it into this fine powder through chemical processing. Pure ZrO2 has three crystal forms: monoclinic, which is stable at room temperature; tetragonal, which is stable above approximately 1170 degrees Celsius; and cubic, which is stable above approximately 2370 degrees Celsius. Pure zirconia wants to change phases when it cools, and that volume jump would shatter it. Adding yttria stabilizes the useful high temperature forms so we can use it at room temperature. Cooling causes tetragonal monoclinic change with 3 to 5% volume expansion, cracks the ceramic. The solution is added 3 to 8% yttria to create yttria stabilized zirconia, YSZ, that stays tetragonal or cubic at room temperature. This phase diagram shows how adding yttria shifts the boundaries so the tough tetragonal phase remains stable down to room temperature. Without it, the material would destroy itself on cooling. So adding yttria, again, lowers the phase transformation temperatures. It allows stable tetragonal or cubic phase temperatures at room temperature. This is the transformation toughening mechanism. Why TZP contains metastable tetragonal grains. A stress at a crack tip triggers tetragonal to monoclinic transformation. Volume expansion compresses and closes the crack. It absorbs the energy and stops crack growth, and this results in high fracture toughness. So when a crack starts, the stress flips the crystal structure right at the tip. The material expands and literally squeezes the crack shut. This self-toughening is why zirconia is so strong and reliable. Thanks to transformation toughening, zirconia combines high strength and toughness with heat resistance and biocompatibility, properties that make it superior for demanding applications. The outstanding properties of yttria stabilized zirconia are high fracture toughness, flexural strength, excellent wear resistance, low thermal conductivity, high melting point, and biocompatible and chemically inert. Let's look at processing of zirconia ceramics. Mining and refining zircon into pure ZrO2 powder. Batching, forming, drying and debinding, sintering at 1400 to 1600 degrees for de-densification, and final machining and polishing if needed. So after purifying the powder, we add the stabilizer and mill it. For thin parts like fuel cell layers, we use tape casting. spreading a slurry and controlling thickness with a doctor blade. The critical step is high temperature sintering, which bonds the particles and locks in the crystal structure. Here's what zirconia looks like after all the manufacturing steps are complete. As you can see, some finished zirconia ceramic components. They are dense, smooth, and white, bright white. They can be made into many different shapes: tubes, plates, rings, blocks, dental crowns, and even complex components for machines. These finished parts are extremely hard, very tough thanks to transformation, toughening, and highly resistant to wear and heat. Because they are also biocompatible, you'll often see them used in dental implants and hip replacements. The transformation from that rough brown zircon mineral and white powder we saw earlier into these precise, strong ceramic components happens through careful powder processing, forming like tape casting and high temperature sintering, the key steps we covered earlier in the presentation. Here are engineering applications of zirconia. Zirconia is used in dental work because it's strong and it looks natural. This is a biomedical use. It can also be used in hip implants. As far as wear parts, it coats jet turbine engines and blades to protect against extreme heat. But one of its most promising uses is in clean energy, solid oxide fuel cells. In a solid oxide fuel cell, the YSZ layer is the heart of the device. It lets oxygen ions pass through while blocking electrons, generating electricity cleanly. The thin layer is made by tape casting a stabilized zirconia slurry and then sintering it to full density. Stacking many cells creates a practical power unit. Again, this thin, dense YSZ layer serves as the solid electrolyte. It allows oxygen ions to flow through at high temperatures. It blocks electrons, forcing them to travel through an external circuit and generate electricity. Then converts hydrogen and oxygen into electricity and water, which is clean, efficient energy. This is manufactured by tape casting a stabilized zirconia slurry followed by high temperature sintering. The finished product is a stacked planar SOFC cells used in power generation systems. In conclusion, in summary, zirconia's crystal magic and smart processing make it one of the toughest and most versatile advanced ceramics available today. Its use in solid oxide fuel cells, SOFC, highlights its role in sustainable energy. Zirconia's phase transformations enable unique transformation toughening. Careful processing, stabilization, and sintering controls its powerful properties. It's excellent for demanding applications, again, especially clean energy solid oxide fuel cells. This is one ceramic with many high-performance engineering uses.